All right, recording has started. Okay, good morning, class. Thank you for coming to today's lesson. You might be surprised of how come there's a change in lecturer. All right, today is me, Dr. Q, Chun Ming, and I'm taking over from Dr. Howard to carry on with the second half of IIoT lessons. And today's lessons is actually a continuation of where Dr. Howard has left off, which is on serial communication. Right, let me do a share screen. Right, so for this morning, I'm taking over from Dr. Howard to carry on to talk about communication. And this part of the communication ties closely to industrial standards. All right, so today we are going to look at field bus. Some of you might have heard about the term field bus and probably would have understood some of these. We are going to look at a different form of communication, in this case, more related to industrial standards. And this is what is being used in the industry. And we term it as field bus. All right, this field bus, I will share more. There are many different types of field bus communication, and we are going to look into some of them, and in particular, Modbus. All right, so first of all, we will be doing a quick recap on what is embedded protocol. Next, today's content will be focusing on industrial communication protocol. All right, why are we looking at this protocol? I will explain. All right, and then subsequently we'll deep dive and focus more on one specific protocol called Modbus. And part of our lab session, we have prepared a Modbus device so that you can actually learn about interfacing with MKR and learn about how to exchange data with this Modbus sensor. I will wrap up today's lesson with talking about what are the upcoming in industrial automations. What is that more commonly accepted protocol, and in this case, the OPC UA standards. All right, so this is the overview of what I will be covering for today's lesson. So let's do a quick recap. I think this is a table to summarize the three serial communication that Prof. Howard had covered with you last week. Just to do a quick wrap up, all right, out of these three serial communication, right, you have one of them being asynchronous, two of them, they are synchronous, right? So this means that they have a common clock, which is SPI and I2C, they have common clock. That's why they can have the synchronous data exchange. So someone must do the timing. But for serial, or we sometimes term this as UART, it does not have a share clock. That's why it is called asynchronous. And for asynchronous communication, the configuration is critical because you need to establish the common baud rate. Baud rate refers to the speed of communication. Next, we also would like you to pay attention to the transmission mode, all right, comparing to full duplex versus half duplex. What do we mean by this? And part of today's lesson, we are going to also discuss this again, okay? Moving down, for embedded communication, we often want to have one-to-one communication. In this case, for serial, is designed for this purpose, all right? And if we look at SPI and I2C, it seems to have a slight extension to one-to-one because for SPI, we can have one master to multiple slave versus I2C that can support multiple master also, okay? For you to be well-versed with Arduino programming and be competent in developing solutions, all right, I've highlighted what are the key functions required to support these serial communications. So namely, the serial, the SPI, and the wire, all right? So these are hyperlinks that will bring you to Arduino reference, and they will bring you to the web page showing you the usage of Arduino functions, these three serial communication functions, how they can be used, and what are their syntax. All right, so back to serial communication. Here is just to highlight some of the key built-in functions, all right, with serial. So serial is an object. It has dot begin, which initialize and configure your serial port. All this while, we have only made use of one input, which is speed. In fact, there are more to just setting the baud rate. You can even configure how many stop bit, all right, whether you want even parity or odd parity, all right? All these configuration would have been covered last week by Dr. Howard. Next, there are other functions. Probably you would have already used the serial dot print, all right? Here, we can also use dot write to write to the transmission buffer, right? Dot read and dot write serve similar functionalities. If you want to receive serial communication data, you use the dot read. Before you can read data, how do you know that there are data coming in? You'll be using the dot available functions to check whether there are data coming in from outside. All right, so these are some of those key functions in serial. And if you click on this hyperlink, you will be able to see more. So let's move on. All right, I've mentioned to you what this configuration is all about already. If there's a need for you to specifically configure, then you need to refer back to serial reference to find out what are the keywords to describe or to set up the configuration. All right, so the configuration come in this standard keywords. You cannot write in your own form, and these are the standard 4 examples that you can use. If you do not put in any configuration over here, all right, by default, it will be a 8-bit non-parity, all right, and 1 stop bit. All right, so the 8 and 1 has a special meaning to the configuration. To find out more, you can go back to serial to have a look. So now that we have discussed what you have learned so far, extending this into the industrial context, there are a few important reasons for this. Firstly, when we look at embedded system, we are looking at small scale, right? We are looking at devices side by side. But once we extend it into the industrial context, into the industry, into the factory, things may not be side by side, right? Devices, machines, equipment can be huge. And that is where the communication path, the distance between machines and equipment can be quite far away. And therefore, whether or not the serial communication can still serve the purpose, and this is where we have to relook at some of those requirements, right? So back to the IIoT, I think this is where we want to first of all learn about the definition. What does the I refers to when we talk about IIoT? And in this case, the I in fact refers to the industrial, all right? So the I refers to industrial, the IoT, the remaining IoT refers to Internet of Things. So this is an extension to talk about smart home usage application, pushing it into the context of the factory. And if you like to find out more, you can read up on definition of I 4.0, which refers to the Industrial Revolution 4.0. Okay, and if you were to trace back, when you read about the history, then that is where some of you would have learned from me about pneumatic controllers, all right, using pressurized air to do automation. And that was the days when electronics wasn't that prominent and it wasn't so cheap. Therefore, a lot of automation is relying on pneumatic. Even for today's context, all right, in food industry where they need cleanliness and hygiene, all right, they are still using pressurized air as the means of the workhorse. All right, instead of electrical power, they are using pressurized air to do automation. But as we know, all right, semiconductor industry has been booming, has been advancing, and now we have AI, machine learning coming into our daily life. So when electronics become cheaper, we are moving away from using pressurized air. And for that, the first protocol that was being adopted was actually the 420 milliamp, all right, the 420 milliamp, which I will elaborate a little bit more in the next few slides. So moving from pressurized air, the next move was actually to make use of electrical current, right? Some of you will be wondering, why use current, all right? There are electrical signal, there are electrical voltage. Why is that not being used? All right, we will talk more in the next few slides. But with some of this implementation, when we talk about massive installation, when there are a lot of devices, equipment, machines talking to one another, some of these are still having their limits, right? Some of the constraints. Therefore, coming to the focus of today's lecture is really on a field bus and why we need to have this protocol. Why do we have to come up with this? This is because we are talking about longer distance of communication, right? More than 1 kilometer. All right, here the communication is not to be confused with telecommunication, which refers to phone calls or even faxing of data and so on. Those were the olden days. But here we are talking about signal from machines to another machines, sharing inputs, outputs, and so on. And we are looking at this kind of distance. All right, data rate, we are looking at 10 to 100 megabits per second. Okay, this is somewhat falling short from where we have or what we have at home already, right? Our broadband are able to transmit even faster than this. And in terms of response time, right, here there are a range of response time between 0.1 second to 1 millisecond. So in this range of response time, it is still deemed as reasonable for use in the industry. However, in the number of devices that we are connecting with, this is really huge. All right, we are talking about having more than thousands of devices connected. You can imagine a campus, all right, with many of you connecting to the Wi-Fi network, right? But in a factory, to have devices, machineries, equipment to be connected, we are also looking at the number in the range of thousands. And there are many different communication protocol being used today, all right? And this may spell some problem also. All right, so therefore, in today's context or in today's lecture, other than talking about what fail bus is, I would also like to share with you the constraint with regards to having too many different protocols altogether. So first of all, we are in an era of a transition, right? The transition between brownfield equipment versus greenfield equipment. There are further elaboration in this hyperlink that I would like you to read out later during the short break. I would like you to spend some time reading this, and then after that, we'll come back to talk about some of these terms. But I want to share with you with regards to this transition because Industrial Revolution, right, started off with steam engine, and then we have electrical power, then we have computers, and today we have IoT and so on. Therefore, there are still very traditional conventional machines around that uses non-standardized communication protocol, right? And when we talk about greenfield refers to an area where you are developing new equipment, and here you are not constrained with any of the backlog. Therefore, for greenfield, you have the luxury to select and choose the kind of standards and specifications. Therefore, in greenfield, it provides a lot of freedom, but freedom comes with responsibility, because if you choose the wrong protocol, wrong specification, then you'll be stuck with that choice for the rest of the time, right? So therefore, it is important to be mindful, all right, how to select the more appropriate protocol. So this part we will revisit after the break to talk about why standardization is important. Okay, what are these equipment and what are greenfield? Now, earlier we have talked about moving from pneumatic system to 420 milliamp. What is this 420 milliamp? All right, if you refer to this chart, it talks about the signal from 4 milliamp all the way up to 20 milliamp. Okay, so this range is the signal that travels through the copper wire, right? This is the signal that travels through the copper wire. Then what is this 4 to 20 milliamp supposed to represent? It represents a signal, all right, over here on the x-axis between 0 to 100%, right? 0 to 100%. And of course, when we talk about this mapping 0 to 100%, it can relate to any sensor signal or command signal that you are trying to manipulate. For example, it could be talking about temperature, all right, temperature. If your temperature range is from 0 to 100 degrees, then this 0 to 100% will be a direct 1:1 mapping. All right, 0% represents 0 degrees, 100% represent 100 degrees. And it can also represent different range, 0 to 100%, representing 0 to 50 degrees Celsius, for example. And then that's where there's a factor of half. But what I want to share with you in this particular slide is that you need to know, all right, that the current that is being transported through the copper wires has to be within 40 to 20. All right, must be between 40 to 20. As I have asked earlier on, why do we choose electrical current versus other electrical properties like voltage? If you recall what you have learned in circuits, we have this KCL. All right, KCL refers to Kirchhoff current law. In a current loop, all right, no matter which part of the loop, the current that flows through that single loop should be the same, right? Because of Kirchhoff current law. And therefore, with these properties, we know that the electrical current will not degrade and it is less susceptible to noise. And that's the reason why we choose 4 to 20 milliamp. Okay. And there are further extension of the use of 420 milliamp standard. And this extension is called the HART, H-A-R-T. And this HART refers to Highway Addressable Remote Transducer. Okay, I highlighted addressable over here is because when you see address or addressable in this case, it refers to the device having a unique ID. And with unique ID, you can actually address the device or call upon this device to interact with you. In the case of doing data exchange, for the sensor, you could be requesting sensor data and so on. All right, in the lab, for the next few days, when you come back to school for your lab sessions, you will see, all right, how a Modbus device can be addressed. How can you call that particular device using its unique ID so that you can extract information from it. And why addressable is useful? Because in a mesh network, just like computers in the internet, you will need to know what is the IP address or DNS domain name when you want to do a search in the web. I mean, in the internet, you will use a web browser or search engine. You will type in some URL, and that URL will point to a specific IP address. All right, so this is the term addressable is supposed to describe. Okay, so I'm going to test you on the understanding, because earlier we talked about the signal. The current has to be between 4 to 20 milliamp. All right. So the question here is asking, if we measure a current of 0 milliamp, what should we understand from 0 milliamp? Okay, if you look at the straight line equation, all right, many of you might have been misled by the dotted line, because if you do extrapolation, all right, extrapolation from this point down, you see that when it is 0 amp, all right, 0 milliamp, it cuts at minus 25. And that's why many of you have selected minus 25. It is wrong, all right, because as part of the 420 milliamp, they deliberately start at 4 milliamp for a very good reason. Okay, so I'm going to explain now. The key reason to have it at 4 milliamp, which establish the zero signal. Okay, let me use my pen. I hope you don't mind that my scribbling with my mouse sometimes can be ugly. Okay, so for mapping 4 milliamp to 0%, this is done deliberately, all right, for a very good reason of the case where we have broken wire. Okay, I say this again. When we receive the lowest signal, which is 0% over here, we must receive 4 milliamp. All right, we must see a 4 milliamp being conducted through the copper wire. And if you ever get zero, if you get 0 milliamp, what can you tell about your copper wire? Right, there must be some breakage, there must be some loose connection. And if that is the case, then this is something that calls for the maintenance team. All right, you should be looking at this part of the system and check why are you not receiving 4 milliamp as the bare minimum. Okay, so this helps the industry to be more prepared for cases of this kind of problem, right? Just imagine in the olden days, there could be pests, rodents, and as you know, rodents like to bite things, and they might be chewing some of your signal wires. And if the signal wires is broken because of this problem, then you know that you have to investigate, because you get 0 milliamp. All right, so therefore, please pay attention to this, as this is the part that sometimes can be confusing. Likewise, on the other part, all right, on the other part or the other extreme, can we have more than 100%? All right, we shouldn't have. And if you measure a current that is more than 20 milliamp, your controller should sound the alarm and investigate on the situation. There could be failure in equipment components that causes extremely high current that's flowing into your copper wires.